In the cathedral of human consciousness, where thoughts echo through the corridors of wonder and doubt, there exists a question so profound it threatens to shatter the very bedrock of reality. What if time itself, that invisible current that sweeps civilizations into dust, that carries newborn stars from their stellar nurseries to their inevitable graves, has no beginning? For generations, humanity has gazed upward at the night sky and whispered the same ancient prayer. Where did it all come from? The answer science gave us seemed almost biblical in its simplicity. 13.8 billion years ago, in a moment smaller than the smallest fraction of a heartbeat, everything that would ever exist burst forth from a point of unimaginable density and heat. The Big Bang, the moment of creation itself. But tonight, in the quiet laboratories where physicists wrestle with equations that describe the birth of space and time, a different truth emerges from the mathematics, like a ghost materializing in moonlight. Hidden within the elegant curves of Einstein's general relativity, concealed in the probabilistic whispers of quantum mechanics, lies a possibility that transforms everything we thought we knew about existence. The eternal universe hypothesis speaks of a cosmos that has no beginning, a universe that has always existed, breathing through infinite cycles of expansion and contraction, each epoch lasting billions upon billions of years before giving way to the next. It suggests that what we call the Big Bang was not a moment of creation, but merely one transition in an endless sequence of cosmic transformations, like waves rolling onto an eternal shore. If this is true, then somewhere in the infinite depths of the past, this exact configuration of matter and energy has occurred before. Every star that burns tonight has burned before. Every thought that crosses a human mind has been thought in identical minds across the vast expanse of eternal time. The universe becomes not a story with a beginning, but an infinite library of all possible stories, each one written and rewritten across the endless pages of time itself. In the quiet corridors of the Catholic University of Louvain, Belgium, during the winter of 1927, a priest named Georges Lemaître bent over mathematical equations that would forever alter humanity's understanding of its place in the cosmos. Lemaître was not seeking to challenge the foundations of existence. He was simply following the mathematical breadcrumbs left by Einstein's general relativity, tracking them through a labyrinth of tensors and field equations that described the curvature of space and time itself. What emerged from those calculations was nothing short of revolutionary. The universe, Lemaître realized, was not the static, eternal cathedral that astronomers had always imagined. It was expanding, growing, larger with each passing moment, its galaxies racing away from one another, like sparks flying from some cosmic forge. The implications struck him like lightning. If the universe was expanding now, then long ago, everything must have been compressed together. Run the cosmic clock backward far enough, and all of creation would converge to what he called the primeval atom, a single point containing all matter and energy that would ever exist. 2 years later, at the Mount Wilson Observatory in California, Edwin Hubble peered through the 100-inch Hooker telescope and confirmed Lemaître's theoretical vision with observational reality. Galaxy after galaxy showed the telltale signature of redshift, their light stretched toward longer, redder wavelengths by the expansion of space itself. The more distant the galaxy, the faster it appeared to be receding, as if the entire universe was inflating like some vast cosmic balloon. Hubble's observations provided the first concrete evidence that the cosmos had a history, that it was not eternal and unchanging but dynamic and evolving. Yet even as this new cosmology took shape, dissenting voices arose from within the scientific community itself. At Cambridge University, 3 brilliant minds, Fred Hoyle, Erman Bondi, and Thomas Gold, gathered in the aftermath of World War II to challenge the emerging consensus. They found something deeply unsatisfying about a universe with a beginning. something that violated their intuitions about the nature of physical law. In 1948, they proposed the steady-state theory, a radical alternative that preserved the idea of an eternal universe. Their model was elegant in its audacity. Yes, the universe was expanding, they acknowledged, but it had no beginning and would have no end. As galaxies moved apart and space expanded, new matter spontaneously appeared in the voids between them, not enough to be detected by any conceivable experiment. Just one hydrogen atom per cubic meter every billion years. This continuous creation maintained the overall density of the cosmos, ensuring that the universe looked the same at all times and in all directions. The steady-state theory proposed that what astronomers observed was not a universe evolving from some primordial birth, but an eternal cosmos in perfect equilibrium, forever renewing itself through the mysterious appearance of new matter. The seeds of this heretical thinking, however, had been planted long before Western science grappled with cosmic origins. In the ancient philosophical traditions of India, cosmologists had described a universe that breathed through vast cycles of creation and destruction. The Puranas spoke of Kalpa's cosmic days, lasting 4.32 billion years, during which the universe would expand and evolve before contracting again into dissolution. These cycles repeated endlessly, with no ultimate beginning or end, only an eternal rhythm of cosmic breathing that stretched across unimaginable spans of time. For centuries, such concepts remained in the realm of philosophy and religion. But as the 20th century progressed and physicists developed increasingly sophisticated mathematical tools for describing the cosmos, some began to wonder whether these ancient insights might contain profound truths about the nature of time itself. The decisive blow to eternal universe theories seemed to come on a spring day in 1965, when two radio astronomers at Bell Telephone Laboratories made an accidental discovery that would earn them the Nobel Prize. Arno Penzias and Robert Wilson were attempting to eliminate interference from their sensitive microwave antenna when they detected a persistent background noise that seemed to come from everywhere in the sky at once. No matter where they pointed their instrument, the signal remained constant, a faint whisper of radiation with a temperature of 2.7 degrees above absolute zero. This cosmic microwave background radiation, as it came to be known, was the afterglow of creation itself, the cooled remnant of the intense heat that filled the universe during its first few 100,000 years of existence. The discovery seemed to provide definitive proof that the Big Bang had actually occurred, that the universe truly did have a moment of birth when space, time, matter, and energy all came into being together. The steady-state theory crumbled before this observational evidence. How could an eternal universe that had always looked the same produce such a specific relic of its own supposed birth? The cosmic microwave background appeared to be the smoking gun that proved the universe had emerged from a hot, dense initial state exactly as Big Bang cosmology predicted. Yet victory brought its own mysteries. As cosmologists delved deeper into the mathematical description of this cosmic birth, they encountered infinities that refused to disappear mathematical singularities, where the equations of general relativity simply broke down. At the moment of the Big Bang itself, the density of matter and the curvature of spacetime became infinite, and the fundamental forces that govern the behavior of particles and fields lost all meaning. Roger Penrose and Stephen Hawking, working together in the 1960s, proved that these singularities were not mere mathematical artifacts that could be eliminated through more careful calculation. Their singularity theorems demonstrated that any universe described by Einstein's general relativity and containing ordinary matter must inevitably contain points where the equations cease to make physical sense, places where space, time, and causality themselves dissolve into meaninglessness. These theorems revealed a profound paradox at the heart of modern cosmology. The same mathematical framework that successfully described the motion of planets, the bending of light around massive stars, and the expansion of the universe also predicted its own failure at the moment of cosmic birth. General relativity pointed toward a beginning that it could not describe, a moment of creation that lay forever beyond the reach of physical law. The implications were both humbling and terrifying. If the universe truly began at a singularity, then the deepest questions about existence, why something exists rather than nothing, what determined the initial conditions that led to stars and galaxies and life itself, might be permanently unanswerable. The moment of beginning appeared to be quarantined from scientific inquiry by the very laws of physics themselves. Yet, some physicists began to suspect that the breakdown of the equations might be revealing something more subtle than the limits of knowledge. Perhaps the singularities were not describing the failure of the universe itself, but the failure of the assumption that time and space must have a beginning. Perhaps the mathematical infinities were nature's way of suggesting that the question itself was flawed, that asking about the beginning of time was like asking about the largest integer or the final digit of pi dot in the quiet moments between calculations. As equations filled blackboards and computer screens, a radical possibility began to whisper through the halls of physics departments around the world. What if the Big Bang was not the beginning of everything, but merely one event in an infinitely longer story? What if time itself had no first moment, no ultimate origin, but stretched backward through eternity like an endless chain of cause and effect? The seeds of heresy had been planted, and they would soon grow into theories that challenged the very foundations of existence itself. The revelation struck the physics community like a thunderclap in a cloudless sky, reverberating through lecture halls and research institutes with a force that shattered centuries of philosophical certainty. At the moment when the universe supposedly began, that infinitesimal point in space and time when everything that would ever exist emerged from nothingness, the elegant mathematical frameworks that had conquered every other mystery of the cosmos simply dissolved into chaos. The singularity at the heart of the Big Bang was not merely another exotic phenomenon to be catalogued and understood. It was something far more disturbing, a place where the fundamental laws of physics ceased to exist, where the very concept of physical law lost all meaning. At this mathematical point of infinite density and temperature, Einstein's equations of general relativity, the same equations that had successfully predicted the existence of black holes, gravitational waves, and the expansion of the universe itself, produced results that made no sense. Division by zero, infinite curvature, mathematical expressions that screamed impossibility in the language of calculus and differential geometry. It was as if physicists had discovered that mathematics itself had been born at a specific moment in time, that the eternal truths of geometry and arithmetic had somehow emerged from a realm where 2 plus 2 equaled both everything and nothing simultaneously. The implications cascaded through every level of understanding like dominoes falling in reverse, each toppled assumption revealing another fundamental mystery. Einstein's theory of general relativity, that masterwork of human reasoning that had revolutionized our understanding of space, time, matter, and energy, contained within its elegant equations the seeds of its own destruction. The theory described how massive objects curve the fabric of space-time, creating the phenomenon we experience as gravity. It explained how the universe expands, how time slows near massive objects, and how light bends around stars. Yet, when applied to the moment of cosmic birth, these same equations pointed toward a mathematical catastrophe, a singularity where the curvature of space-time became infinite and prediction became impossible. The crisis was not limited to general relativity. Quantum mechanics, that other pillar of modern physics that governs the behavior of particles and fields at the smallest scales, offered no refuge from the conceptual chaos. Quantum theory describes a universe where probability reigns supreme, where particles exist in superposition until measured, where the very act of observation shapes reality. But quantum mechanics requires a stage upon which this probabilistic drama can unfold. It needs space and time as a backdrop for its uncertainty principles and wave functions. If space and time themselves began at the Big Bang, then quantum mechanics, like general relativity, had no foundation upon which to stand. The philosophical implications struck deep into the heart of scientific methodology itself. For centuries, science had progressed through the systematic application of reason to observation, building mathematical models that could predict and explain natural phenomena. The great triumphs of physics, from Newton's laws of motion to Maxwell's electromagnetic theory to Einstein's relativity, had all shared a common characteristic. They were universal, applying equally at all times and in all places. But the Big Bang singularity seemed to suggest that there was a moment when no laws applied, a time before time when neither logic nor mathematics held sway. Stephen Hawking, perhaps the most eloquent voice of modern cosmology, captured the essence of this crisis with characteristic precision. Standing before audiences of physicists and philosophers, he would pose the question that haunted every attempt to understand cosmic origins. If the universe had a beginning, what happened before the beginning? The question seemed to answer itself through its own logical structure. If time itself began with the universe, then the concept of before became meaningless, like asking, what lies north of the North Pole, or what color is the number 7 dot? Yet even Hawking found this answer unsatisfying. The mathematical mind rebels against such conceptual barriers, sensing that they might reflect not the ultimate limits of reality, but the limitations of current understanding. If the deepest questions about existence were rendered meaningless by the structure of the questions themselves, then perhaps the structure needed to be questioned rather than the existence it sought to understand. The breakdown at the Big Bang singularity revealed something profound about the nature of scientific knowledge itself. The equations of general relativity were not failing because they were wrong. They continued to describe the Themistian behavior of gravity with extraordinary precision. In every other context, they were failing because they were being asked to describe something that might not exist, the beginning of time itself. This was not merely an academic puzzle to be solved in the comfort of university offices and research institutes. The crisis struck at the foundation of the scientific worldview, suggesting that there might be aspects of reality that would remain forever beyond the reach of human understanding. If the origin of the universe lay on the far side of a mathematical singularity, then cosmology had encountered a boundary as absolute as the event horizon of a black hole, a point beyond which no information could ever travel. The implications were both humbling and terrifying. Humanity had spent centuries building an increasingly sophisticated understanding of the natural world, developing theories and technologies that allowed civilization to split atoms, explore other planets, and peer into the deepest structures of matter and energy. Yet all of this accumulated knowledge seemed to stop at a single point in spacetime, as if there existed a cosmic quarantine that separated the knowable from the unknowable. Some physicists found themselves confronting an almost theological crisis. If the universe truly emerged from a state that transcended physical law, then science had inadvertently rediscovered something resembling the traditional concept of divine creation, a moment when natural forces gave way to something beyond nature itself. The mathematics seemed to be pointing toward a realm that could only be described in the language of miracle rather than mechanism. Others reacted with a different kind of philosophical discomfort. The idea that fundamental questions about existence might be permanently unanswerable violated the core assumption of scientific progress, that persistent inquiry and increasingly sophisticated tools would eventually illuminate every mystery. If the Big Bang singularity truly represented an impenetrable barrier to understanding, then human reason had encountered its ultimate limit. Yet in the quiet corners of physics departments around the world, a small but growing group of theorists began to consider a radical alternative. What if the mathematical breakdown at the Big Bang was not revealing the fundamental limits of physical law, but the fundamental flaw in the assumption that time must have a beginning? What if the singularity was not describing a moment when physics failed, but a mathematical artifact produced by the incorrect assumption that the universe was born rather than eternal? The equations themselves seem to whisper this possibility. When mathematicians encounter infinities in their calculations, they often signal that the wrong questions are being asked or that inappropriate assumptions are being made. Perhaps the infinite density and temperature at the Big Bang were not describing a real physical state, but mathematics' way of rejecting the premise that led to such impossible results. In the laboratories where particle accelerators probe the fundamental forces of nature, in the observatories where telescopes peer into the deepest reaches of space and time, and in the theoretical physics institutes where equations map the architecture of reality itself, a heretical thought began to take shape. If the breakdown of physical law at the Big Bang was truly unbearable to the scientific mind, then perhaps the solution was not to accept the breakdown, but to question the beginning itself. The crisis had planted the seeds of its own resolution. If physics could not describe the birth of time, perhaps it was because time had no birth to describe. If the equations broke down at the moment of creation, perhaps it was because there was no moment of creation to break down at. The mathematical singularity that seemed to quarantine the origin of the universe from scientific understanding might instead be pointing toward a universe that had no origin to quarantine, a cosmos as eternal and beginningless as the mathematical. Truths that described its behavior. In the face of this crisis, the scientific community stood at a crossroads. One path led toward accepting fundamental limits to human knowledge, embracing mystery as an irreducible feature of existence. The other path led toward questioning the assumptions that had created the mystery in the first place, toward theories that would preserve the universality of physical law by denying the reality of cosmic birth altogether. In the closing decades of the 20th century, as humanity's technological reach extended ever deeper into the cosmos, a new generation of instruments began to decipher the ancient language written in light across the universe. These were not merely telescopes, but time machines, devices capable of reading the fossil record of creation itself, etched in radiation that had been traveling through space for billions of years before the first stars were even born. The Cosmic Background Explorer, launched by NASA in 1989, carried into orbit the most sensitive instruments ever designed to study the cosmic microwave background, that faint afterglow of the Big Bang that permeates every cubic centimeter of space. For 14 months, COBE mapped the temperature of this primordial radiation with unprecedented precision, revealing the universe as it existed when it was only 380,000 years old, when the cosmos had finally cooled enough for atoms to form and light to travel freely through space for the first time. What COBE discovered was both a confirmation and a mystery. The cosmic microwave background was indeed nearly uniform in temperature, 2.725 degrees above absolute zero in every direction, exactly as Big Bang theory predicted. But hidden within this uniformity were tiny fluctuations, temperature variations, of only a few millionths of a degree that told a story of cosmic evolution more complex than anyone had imagined. These minute temperature differences were the seeds from which all structure in the universe would eventually grow, the primordial whispers that would amplify over billions of years into galaxies, stars, and planets. The Wilkinson Microwave Anisotropy Probe, launched in 2001, carried this investigation to even greater depths of precision. WMV spent 9 years mapping these cosmic temperature variations with exquisite detail, creating the most ancient baby picture of the universe ever captured. The data revealed patterns in the cosmic microwave background that were simultaneously beautiful and troubling harmonic oscillations that spoke of sound waves rippling through the primordial plasma, but also anomalies that challenged the simple narrative of cosmic birth. That a horizon problem emerged as one of the most perplexing puzzles in all of cosmology. When astronomers looked at opposite sides of the cosmic microwave background regions of space, separated by distances so vast that light from one side could never have reached the other during the 380,000 years since the Big Bang, they found identical temperatures. How could regions that had never been in causal contact, that had existed in complete isolation from one another since the moment of creation, display such perfect thermal equilibrium? It was like discovering that two isolated laboratories on opposite sides of the Earth had independently arrived at identical room temperatures, down to the thousandth of a degree, without any possible means of communication between them. The precision of this cosmic coordination suggested either an incredible coincidence or a fundamental gap in the understanding of cosmic history. The flatness problem presented an equally troubling mystery. Einstein's general relativity allows for universes with 3 possible geometries. They can be curved like the surface of a sphere, curved like the surface of a saddle, or perfectly flat like an infinite sheet of paper. The WMAP observations revealed that our universe was flat to within a margin of error so small that it defied statistical probability. At the moment of the Big Bang, the initial conditions would have needed to be fine-tuned to an accuracy of 1 part in 1060, a precision so extreme that writing it out in decimal notation would require more digits than there are atoms in the observable universe. These discoveries led cosmologists to propose one of the most radical theories in the history of science: cosmic inflation. Alan Guth, working at Stanford University in 1980, suggested that during the first tiny fraction of a second after the Big Bang, between y-36 and 10.32 seconds after creation, the universe underwent a period of exponential expansion more violent than anything in the subsequent history of the cosmos. During this inflationary epoch, space itself expanded faster than the speed of light, growing by a factor of at least 1026, in less time than it takes light to cross the diameter of a proton. Inflation solved both the horizon and flatness problems with mathematical elegance. Regions that appeared to have never been in causal contact had actually been close neighbors before inflation stretched them to opposite sides of the observable universe. The universe appeared flat because inflation had stretched any initial curvature to the point where it became undetectable, like the way the surface of the Earth appears flat to an ant walking across it. But inflation created new mysteries, even as it solved old ones. The theory required the existence of an inflattened field, a quantum field, that permeated all of space and drove the exponential expansion through its potential energy. As this field evolved and eventually decayed, it released enormous amounts of energy that heated the universe and created the hot, dense conditions of the traditional Big Bang model. The mathematics of inflation, however, suggested something deeply unsettling. If inflation could occur once, there was no obvious mechanism to prevent it from occurring again and again. In fact, the quantum nature of the inflattened field meant that inflation might be eternal, constantly creating new regions of space-time through quantum fluctuations, with each new region potentially evolving into its own observable universe. This eternal inflation scenario transformed the Big Bang from a unique moment of creation into just one event in an infinite series of cosmic births. The universe became not a single expanding bubble of space-time, but an infinite multiverse containing countless pocket universes, each with its own Big Bang, its own physical laws, and its own evolutionary history. Quantum mechanics added another layer of strangeness to this already bewildering picture. In the quantum realm that governs the behavior of subatomic particles, the vacuum of space is not empty, but seething with virtual particles, pairs of matter and antimatter that spontaneously appear and disappear, borrowing energy from the quantum vacuum for brief moments before annihilating each other and returning that energy to the void. The Heisenberg uncertainty principle allows such quantum fluctuations to violate the conservation of energy, but only temporarily and only for durations inversely proportional to the amount of energy borrowed. Small fluctuations can persist for relatively long times, while large fluctuations must disappear almost instantly. But at the moment of cosmic birth, when the entire observable universe was compressed to quantum dimensions, these same principles might have allowed the ultimate quantum fluctuation, the spontaneous appearance of an entire universe from the vacuum of space-time. This quantum origin model suggested that the universe was not created by some external cause, but rather emerged as a natural consequence of quantum mechanics itself. The cosmos became a self-bootstrapping system, borrowing its entire mass energy from the quantum vacuum and spending the subsequent billions of years paying back that cosmic debt through the expansion of space and the cooling of matter. Particle accelerators, like the Large Hadron Collider, began probing the high-energy physics that would have dominated the first moments after the Big Bang, recreating in miniature the conditions that existed when the universe was less than a trillionth of a second old. Each new particle discovered, each new force unveiled, painted a picture of a cosmos governed by laws that became increasingly exotic as physicists pushed closer to the moment of creation. The discovery of the Higgs boson in 2012 revealed the existence of fields that permeate all of space and give particles their mass. But these same field theories suggested that the vacuum of space might exist in multiple states, stable and metastable configurations that could transition from one to another through quantum tunneling events. If the current vacuum state was metastable, then it might eventually decay into a more stable configuration, triggering a cosmic phase transition that would propagate outward at the speed of light, fundamentally altering the laws of physics and potentially destroying everything in its path. String theory emerged as perhaps the most ambitious attempt to resolve the mathematical contradictions that plagued cosmological models of the Big Bang by replacing point particles with extended objects, one-dimensional strings. Vibrating in higher-dimensional space string theory promised to eliminate the infinities that appeared in conventional quantum field theories and provide a unified description of all fundamental forces. Some versions of string theory suggested that the Big Bang was not a moment of creation, but a transition, a cosmic bounce that occurred when the universe rebounded from a previous phase of contraction. In these models, space and time were eternal, cycling through endless periods of expansion and contraction, with each bounce creating the conditions that observers in the subsequent expansion would interpret as the beginning of everything. The mathematics of string theory opened up possibilities that stretched the imagination beyond its breaking point. The theory required additional spatial dimensions beyond the three that humans could directly perceive, folded up into geometries so small and complex that they remained hidden from ordinary experience. In this higher dimensional landscape, what appeared to be the birth of the universe might be merely the intersection of multidimensional brains, vast surfaces floating in hyperspace whose collisions could trigger the explosive expansion that cosmologists observed as the Big Bang. As the 21st century progressed and observations became more precise, the simple story of cosmic birth grew ever more complex. Each new discovery seemed to push the moment of true beginning further into the past, replacing it with earlier and earlier processes that themselves required explanation. Inflation preceded the Big Bang. Quantum fluctuations preceded inflation. String dynamics preceded quantum fluctuations, and in the mathematical depths of these theories, physicists began to glimpse the possibility that the chain of causation might extend backward through time without ever reaching a first link. The universe revealed through these investigations was not the straightforward product of a moment of creation, but something far stranger and more wonderful, a cosmos whose origins receded like a mirage, always seeming to lie just beyond the reach of the next theoretical breakthrough or observational advance. In the quantum whispers and cosmic echoes detected by humanity's most sophisticated instruments, the eternal universe hypothesis found not proof, but possibility, the suggestion that time itself might be as beginningless as the mathematical truths used to describe its passage. As cosmologists ventured deeper into the mathematical landscape of eternal time, they found themselves standing at the edge of an intellectual abyss that threatened to swallow not just their theories, but their sanity itself. The concept of an eternal universe was not merely another scientific hypothesis to be tested and refined. It was a doorway into the realm of actual infinity, a mathematical territory where intuition breaks down and paradoxes multiply like fractals, each one spawning infinite variations of impossibility. To contemplate a universe without beginning is to wrestle with infinity in its most naked and unforgiving form. If time stretches backward without end, then the cosmos becomes an infinite library containing not just every story that has ever been told, but every story that could possibly be told, written in the language of matter and energy across the endless pages of space and time. In such a universe, nothing is unique, nothing is unprecedented, and nothing happens only once. The implications cascade through the foundations of existence, like dominoes falling in reverse through eternity. If the universe has indeed existed for an infinite duration, then every possible arrangement of atoms, every conceivable configuration of matter and energy, must have occurred not just once, but infinitely many times. The conversation occurring at this very moment, these exact words, spoken in this precise sequence, has already taken place in countless identical worlds, scattered throughout the infinite expanse of time and space. Somewhere in the infinite past, an identical Earth orbited an identical sun, populated by identical beings, living identical lives, making identical choices, and contemplating identical questions about the nature of time and existence. That world experienced the same droughts and floods, the same wars and peace, the same discoveries and forgettings that mark the human story. Every joy experienced here has been experienced infinitely before. Every tragedy endured here has been endured infinitely before. Every moment of wonder and confusion and love has echoed through eternity, like light bouncing between infinite mirrors. This infinite repetition extends beyond mere human experience into the deepest structures of reality itself. If time is truly endless, then identical galaxies must have formed and dissolved countless times. Identical stars must have been born and died in infinite cycles, and identical planets must have spawned identical forms of life that asked identical questions about their origins and purposes. The universe becomes not a unique creation, but an eternal performance, playing the same cosmic symphony over and over again across the infinite stages of space and time. Yet this infinite repetition spawns paradoxes that challenge the very foundations of physical law. If the universe has existed forever, why hasn't it reached thermal equilibrium, that final state of maximum entropy, where all energy is evenly distributed and no further work can be done? According to the second law of thermodynamics, isolated systems always evolve toward greater disorder, dissipating useful energy into waste heat until they reach a state of perfect thermal balance. In an infinite universe with infinite time, This process should have been completed long ago, leaving behind a cold, dark cosmos where nothing interesting could ever happen again. This temporal extension of Olber's paradox, the question of why the night sky is dark in an infinite universe, becomes even more troubling when applied to time rather than space. If the universe contained infinite energy distributed across infinite time, then every point in space would be blazing with the accumulated radiation of infinite stellar burning. The darkness of the night sky becomes not just a mystery, but an impossibility, as inexplicable as finding silence in a concert hall filled with infinite orchestras playing simultaneously. The concept of infinite regression haunts every attempt to understand causation in an eternal universe. If every event is caused by previous events, and this chain of cause and effect extends backward through infinite time, then how can the causal structure of reality ever be understood? The universe becomes like a book with infinite chapters, each one necessary to understand the next, but with no first page upon which to begin reading. Every explanation requires a prior explanation. Every cause requires a prior cause. And the search for ultimate understanding recedes infinitely into the past like a horizon that retreats no matter how far one travels toward it. The modern observations have revealed yet another layer of complexity in this infinite puzzle. The discovery of dark energy, that mysterious force driving the accelerating expansion of the universe, suggests that space itself is imbued with an intrinsic energy density that remains constant even as the universe expands. Unlike matter and radiation, which become more dilute as space grows, dark energy maintains its density, causing the rate of cosmic expansion to increase exponentially over time. If this acceleration continues unchanged, it will lead inevitably to what cosmologists call the Big Rip scenario, in which the expansion of space eventually overcomes all the fundamental forces that hold matter together. First, galaxy clusters will be torn apart as the space between them expands faster than gravity can pull them together. Then, individual galaxies will be shredded, followed by solar systems, planets, and finally atoms themselves, as the fabric of space-time expands so rapidly that no structure can maintain its coherence. This cosmic ending would seem to place a definitive limit on the future of the universe, suggesting that even if time had no beginning, it might indeed have an end. The eternal universe would become only semi-eternal, stretching infinitely into the past, but terminating in a finite future when the last atoms are torn apart by runaway expansion. Yet even this apparent cosmic death might be nothing more than an illusion, another transition in an infinitely cycling process. Quantum mechanics reveals that the vacuum of space is not truly empty, but seethes with virtual particles and quantum fluctuations that borrow energy from nothingness before returning it, in accordance with Heisenberg's uncertainty principle. On infinite timescales, these quantum fluctuations become not just possible, but inevitable, no matter how improbable they might seem in any finite duration. Given infinite time, quantum mechanics virtually guarantees that fluctuations large enough to create new Big Bangs will eventually occur, emerging spontaneously from the quantum vacuum like flowers blooming in an infinite garden of possibility. The Big Rip that destroys one universe becomes the quantum foam from which new universes are born, each one destined to expand, evolve, and eventually tear itself apart before giving birth to its successors. The mathematics of eternal inflation carries these concepts to their ultimate logical conclusion. In this framework, our entire observable universe, all the galaxies and stars and planets we can see with our most powerful telescopes, represents nothing more than a single bubble in an infinite cosmic foam. This bubble formed when a region of space underwent a brief period of exponential expansion, creating the conditions we observe as the Big Bang. But this process of cosmic bubble formation never stops. throughout the infinite expanse of space-time. Quantum tunneling events constantly trigger new episodes of inflation, each one creating a new pocket universe with its own Big Bang, its own physical constants, and its own evolutionary history. Some of these bubble universes might be similar to our own, governed by familiar laws of physics and populated by stars and planets and possibly life. Others might be utterly alien, operating according to physical principles so different from our own that they would be unrecognizable as universes at all. In the eternal inflation scenario, what humans call the Big Bang, that moment 13.8 billion years ago, when our observable universe began its expansion, becomes not the beginning of everything, but merely a local event in an infinitely larger and older cosmos. The universe as a whole has no beginning because it is constantly beginning, always creating new regions of space-time that will interpret their own origins as the moment when time itself was born. This infinite multiverse spawns infinite versions of every possible world. There are bubble universes where the fundamental constants of nature are slightly different, leading to stars that burn differently and planets that orbit differently and life that evolves differently. There are universes where the strong nuclear force is weaker, preventing the formation of complex nuclei, and universes where gravity is stronger, causing matter to collapse into black holes before stars can form. But there are also universes, identical to our own in every detail, where identical versions of every person live identical lives and make identical discoveries about the infinite nature of reality. The contemplation of eternal time becomes not just a scientific endeavor, but a meditation on the infinite nature of existence itself. A recognition that consciousness might be as eternal and inevitable as the mathematical truths that describe the behavior of matter and energy. In this infinite cosmos, the question of whether time has a beginning transforms from a scientific problem into a philosophical paradox that illuminates the deepest mysteries of existence. The search for cosmic origins becomes a journey not toward a moment of creation, but toward an understanding of how finite minds can comprehend infinite realities, how temporary consciousness can grasp eternal truths, and how singular experiences can emerge from an endlessly repeating multiverse, where everything that can happen must happen, and everything that has happened must happen again. From the mathematical chaos that emerges when confronting infinite regression, theoretical physicists began to weave new frameworks of understanding, elegant mathematical architectures that could house the concept of eternity without collapsing under the weight of their own paradoxes. These theories emerged not as desperate attempts to solve unsolvable puzzles, but as natural extensions of the deepest insights into the nature of space, time, matter, and energy that human science had achieved. The cyclic universe model arose, like a phoenix from the ashes of the Big Bang singularity, transforming what had seemed like a moment of cosmic birth into an eternal rhythm of expansion and contraction that had been beating like a universal heartbeat since before time began. Paul Steinhardt of Princeton University and Neil Turok of Cambridge University developed this elegant framework in the early years of the 21st century, drawing upon the mathematical foundations of string theory and min theory to construct a vision of cosmic evolution that had no beginning and would have no end. In their model, the Big Bang was not a moment of creation, but a transition, a cosmic bounce that occurred when the universe rebounded from a previous phase of contraction into its current phase of expansion. Like a ball that bounces eternally between two walls, the universe oscillated through endless cycles of growth and shrinkage, each cycle lasting trillions of years and separated from the next by the violent but brief transition that cosmologists had mistaken for the birth of everything. The mathematical foundation for this cyclical cosmos lay in the revolutionary concepts of string theory and its extension into myth theory, which suggested that the familiar three dimensions of space, plus one dimension of time that define human experience were merely projections of a far richer reality. In this higher dimensional framework, the entire observable universe might be nothing more than a membrane, a brain, floating in an 11-dimensional hyperspace populated by other brains, each one potentially harboring its own universe with its own physical laws and evolutionary history. The cyclic model proposed that the Big Bang occurred when two of these brains collided in the higher dimensional space, releasing enormous amounts of energy that manifested as the hot, dense conditions that marked the beginning of cosmic expansion. As the universe expanded and cooled over billions of years, the brains gradually separated, carried apart by forces operating in the extra dimensions. Eventually, the expansion would slow, stop, and reverse, drawing the brains back together for another collision that would trigger the next cycle of cosmic evolution. This elegant dance of brains in higher dimensional space transformed the apparently unique event of cosmic birth into one movement in an eternal ballet, with each collision generating conditions that would be interpreted by inhabitants of the resulting universe as the beginning of time itself. The cyclic model preserved the observational successes of Big Bang cosmology while eliminating the troublesome singularity that had marked the breakdown of physical law at the moment of supposed creation. Eternal inflation offered a radically different vision of timelessness, one that emerged naturally from the mathematical structure of the inflation theory itself. When Alan Guth first proposed cosmic inflation in 1980, he envisioned it as a brief episode in the first fraction of a second after the Big Bang, a period of exponential expansion that lasted perhaps 10 to 32 seconds before ending and giving way to the more sedate expansion described by standard Big Bang cosmology. But as Andrew Lind and other theorists developed the mathematics of inflation more fully, they discovered that ending inflation was actually more difficult than starting it. The inflated field that drove the exponential expansion of space was subject to quantum fluctuations that could cause different regions of space-time to evolve at different rates. While inflation ended in our local region of the universe 13.8 billion years ago, it continued and continues still in countless other regions throughout the infinite expanse of space-time. The result is a cosmic structure of staggering complexity, an eternally inflating multiverse in which new pocket universes are constantly being born through quantum fluctuations, each one destined to evolve its own galaxies, stars, and possibly life. In this eternal inflation scenario, what humans observe as the Big Bang was merely a local event, the moment when inflation ended in their particular region of space-time, and the energy of the inflated field was converted into the hot, dense matter and radiation of the traditional Big Bang model. But the multiverse as a whole had no beginning, having been inflating eternally into the past, constantly creating new pocket universes that would each interpret their own local conditions as the origin of everything. This model suggested that time itself had no beginning because the process of creating time, the initiation of new regions of space-time through quantum fluctuations in the inflated field, had been occurring forever. The eternal inflation multiverse became a cosmic factory for producing Big Bangs, each one marking not the birth of time, but the birth of a new timeline within an already existing eternal framework. Quantum cosmology pushed these concepts into even stranger territory, questioning not just when time began, but whether the question itself made sense within the framework of quantum mechanics. James Hartle of the University of California and Stephen Hawking developed what became known as the no-boundary proposal, suggesting that the universe emerged not from a classical singularity, but from a quantum superposition of all possible initial conditions. In this framework, the universe had no more need for a beginning than an electron had need for a definite position before measurement. The mathematical heart of quantum cosmology lay in the Wheeler-DeWitt equation, sometimes called the Schrödinger equation of the universe. Just as the ordinary Schrödinger equation describes how quantum wave functions evolve through time, the Wheeler-DeWitt equation was intended to describe how the wave function of the entire universe evolved. But this created a profound conceptual puzzle. Evolution requires time, yet if the universe itself was described by a wave function, what provided the time parameter for cosmic evolution? Some interpretations suggested that time itself was an emergent property, an illusion that arose from the correlations between different parts of the universal wave function rather than a fundamental aspect of reality. In this view, duration was not a stage upon which cosmic evolution played out, but a byproduct of the quantum entanglement between different regions of space and different configurations of matter and energy. Time became not a river flowing from past to future, but a pattern woven into the fabric of quantum correlations that defined the structure of reality itself. The timeless nature of the universal wave function suggested that all moments past, present, and future existed simultaneously within the quantum description of the cosmos. The apparent flow of time from past to future was a consequence of the way conscious observers were embedded within particular regions of the wave function, experiencing the correlations between different quantum states as temporal sequences, when they were actually aspects of a static, eternal mathematical structure. Loop quantum cosmology emerged from the attempt to apply the principles of loop quantum gravity to the entire universe, offering yet another pathway to understanding how time might exist without beginning. In this framework, space and time themselves were quantized, composed of discrete, indivisible units at the smallest possible scales, just as matter and energy were composed of discrete particles and quanta. The quantization of space-time had profound implications for cosmic origins. The apparent singularity of the Big Bang, that mathematical point where density and temperature became infinite, was revealed to be an artifact of treating space and time as continuous rather than quantized. When the discrete nature of space-time was taken into account, the singularity dissolved into a quantum bounce, a smooth transition from a previous contracting phase of the universe to the current expanding phase. In loop quantum cosmology, the Big Bang became the Big Bounce, a moment when the universe transitioned from contraction to expansion without ever reaching a state of infinite density or temperature. The mathematical breakdown that had plagued conventional cosmology was eliminated by recognizing that space and time themselves had a granular structure at the smallest scales, preventing the formation of true singularities where physical law would cease to apply. This quantum bounce could occur repeatedly, creating a cyclic universe that oscillated between phases of expansion and contraction without ever reaching the mathematical extremes that marked the limits of classical general relativity. Each bounce would appear to inhabitants of the subsequent expansion as the beginning of their universe, but the cosmos as a whole would be eternal, cycling through endless phases of growth and shrinkage like a cosmic lung breathing through infinite time. These theoretical frameworks, cyclic brains colliding in higher dimensions, eternal inflation creating infinite pocket universes, quantum superpositions eliminating the need for classical beginnings, and quantized space-time preventing singular birth moments all pointed toward the same radical conclusion. The apparent beginning of time might be nothing more than a conceptual artifact arising from the limitations of classical thinking applied to quantum and relativistic phenomena. Each theory offered its own vision of eternity's architecture, its own mathematical framework for understanding how a universe could exist without ever having been born. Yet they all shared a common insight that the deepest questions about cosmic origins could not be answered within the conceptual frameworks that had given rise to those questions in the first place. Understanding the nature of time's beginning required abandoning the assumption that time must have a beginning to understand God in the mathematical realms explored by these theories. Time became not a river with a source, but an ocean without shores vast, deep and eternal, supporting infinite possibilities for cosmic evolution and conscious experience. The search for the moment when time began transformed into a recognition that time itself might be as eternal and beginningless as the mathematical truths that described its passage. In the first decades of the 21st century, the question of time's beginning has transformed from the province of philosophers and theologians into the domain of experimental science. Across the planet, in laboratories buried deep underground, in observatories perched on remote mountaintops, and in spacecraft sailing through the cosmic void, humanity has deployed an arsenal of instruments capable of probing the deepest mysteries of existence itself. These technological marvels represent more than mere tools of observation. They are humanity's attempt to reach backward through time and touch the face of eternity. The James Webb Space Telescope, launched on Christmas Day 2021, floats at the second Lagrange point, a gravitationally stable region of space where the pull of Earth and Sun balance in perfect equilibrium. From this cosmic vantage point, JWST peers deeper into space and further back in time than any instrument before it. Its golden mirrors collecting photons that have been traveling through the universe for more than 13 billion years. These ancient messengers of light carry within their wavelengths the encoded history of cosmic evolution, revealing galaxies as they existed when the universe was barely 5% of its current age. But JWST is searching for more than distant galaxies and early stars. Hidden within the spectra of the most ancient light, astronomers hope to find signatures of pre-Big Bang physics, subtle anomalies in the distribution of matter and energy that might preserve information about what came before the supposed moment of creation. If the universe is truly eternal, cycling through endless phases of expansion and contraction, then the initial conditions observed by JWST should bear the imprint of previous cosmic epochs, like geological strata that preserve the history of ancient worlds. The telescope's unprecedented infrared vision is revealing galaxies that formed within the first few 100 million years after the Big Bang. During the epoch cosmologists called Cosmic Dawn, these primordial stellar nurseries appear surprisingly mature and massive, challenging conventional models of cosmic evolution and suggesting that the early universe might have been more complex and structured than previously imagined. Each new observation pushes the frontier of known cosmic history further into the past, approaching ever closer to that mysterious moment when time itself supposedly began. The European Space Agency's Planck satellite, which concluded its mission in 2013 after 4 years of observations, created the most detailed map of the cosmic microwave background ever achieved. This ancient radiation, the afterglow of the Big Bang itself, carries within its temperature fluctuations the fossil record of the universe's first moments. Planck's instruments, sensitive to temperature variations of mere microkelvin, searched for the characteristic signature of primordial gravitational waves ripples in spacetime that would have been generated during the epoch of cosmic inflation. These gravitational waves, if they exist, would appear as a specific pattern of polarization in the cosmic microwave background, a swirling signature etched into the fabric of spacetime itself. Their detection would provide direct evidence of inflation and potentially reveal whether the Big Bang was preceded by other events. The pattern would serve as a cosmic fingerprint, preserving information about the quantum fluctuations that occurred during the first fraction of a second after the supposed beginning of time. On Earth, gravitational wave detectors like LIGO in the United States and Virgo in Europe have opened an entirely new window into the cosmos. These extraordinary instruments use laser interferometry to detect the infinitesimal stretching and compression of spacetime caused by passing gravitational Waves measuring distortion smaller than 1/10,000th the width of a proton. While LIGO and Virgo have primarily detected gravitational waves from colliding black holes and neutron stars, they represent the vanguard of a new era in astronomy, one that observes the universe through ripples in spacetime rather than electromagnetic radiation. The planned Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will extend gravitational wave astronomy into space, where it can detect much longer wavelength signals from cosmic sources that occurred billions of years ago. Some eternal universe models predict specific patterns of gravitational waves that could distinguish between different scenarios for cosmic origins, signatures that might reveal whether our Big Bang was unique or merely one event in an endless series of cosmic transitions. Deep beneath the European countryside, the Large Hadron Collider continues to push the boundaries of high-energy physics, accelerating protons to energies approaching those that existed during the first moments after the Big Bang. The LHC's discovery of the Higgs boson in 2012 confirmed the existence of the field that gives particles their mass, completing the standard model of particle physics. But this achievement also revealed new mysteries about the fundamental nature of space and time. The Higgs field that permeates all of space exists in what physicists call a metastable state, stable for now, but potentially capable of transitioning to an even lower energy state through quantum tunneling. If such a transition occurred, it would propagate outward at the speed of light as a bubble of altered spacetime, fundamentally changing the laws of physics and potentially destroying everything in its path. This vacuum decay scenario suggests a mechanism by which new Big Bang events could be triggered, creating fresh regions of spacetime with different physical constants and evolutionary histories. Future particle accelerators, if they are ever built, might probe even higher energy scales, approaching the conditions that existed during the hypothetical epoch of cosmic inflation. These machines would not just recreate the physics of the early universe. They might actually create miniature universes, testing whether the quantum fluctuations that drive eternal inflation can be generated and controlled in terrestrial laboratories. In the realm of theoretical physics, supercomputer simulations are modeling the behavior of quantum fields in curved spacetime, seeking to understand how the fundamental forces of nature behaved during the extreme conditions near the Big Bang. These computational experiments test whether eternal inflation naturally emerges from realistic initial conditions, exploring how quantum fluctuations in the inflated field could generate the endless series of pocket universes predicted by the theory. The simulations also investigate how information might propagate between different cycles in a cyclic universe, addressing the question of whether observational signatures from previous cosmic epochs could survive the violent transition through a Big Bang event. If such signatures exist, they would provide direct evidence for the eternal nature of cosmic evolution, preserved like messages in bottles washing ashore from an infinite ocean of time. String theory continues its mathematical evolution, with theorists developing new insights into how the extra dimensions required by the theory might influence cosmic evolution. Recent work suggests that string theory naturally leads to eternal or cyclic cosmologies, with the dynamics of higher dimensional brains driving endless cycles of cosmic expansion and contraction. These mathematical frameworks are being tested against observational data, searching for signatures of extra dimensions in the cosmic microwave background and in the behavior of fundamental particles. The search for dark matter and dark energy represents another crucial frontier in understanding cosmic origins. Underground detectors, like the Xenon experiment in Italy and the Lux Zeppelin detector in South Dakota, are searching for weakly interacting massive particles that might comprise the invisible matter that outweighs ordinary atoms by a factor of 5 to 1. Space-based missions like the Euclid telescope are mapping the large-scale structure of the universe with unprecedented precision, seeking to understand the nature of the dark energy that drives accelerating cosmic expansion. Understanding dark energy is particularly crucial for determining the ultimate fate of the universe and whether cosmic expansion will continue forever or eventually give way to new phases of evolution. If dark energy represents a fundamental property of space itself, then the universe might expand exponentially into an empty future, with quantum fluctuations eventually triggering new Big Bang events in the infinite expanse of time ahead. If dark energy is a temporary phenomenon associated with a slowly evolving field, then the current epoch of accelerating expansion might be a brief interlude in a more complex cosmic story. The Varro Rubin Observatory in Chile, currently under construction, will survey the entire visible sky every few days, creating a four-dimensional map of the universe that captures both spatial structure and temporal evolution. This unprecedented dataset will reveal how cosmic structure has evolved over billions of years, potentially uncovering signatures of cyclical evolution or eternal inflation that have been hidden within the statistical properties of galaxy distributions and cosmic web architecture. As these instruments push deeper into space and further back in time, they are not merely collecting data, but participating in humanity's most ambitious quest, the attempt to understand whether existence itself had a beginning or has always been. Each new observation, each theoretical breakthrough, each computational simulation adds another piece to the cosmic puzzle, bringing science closer to answering the ultimate question of whether time stretches infinitely into the past or emerged from nothingness in a singular moment of creation. The tools of modern cosmology have transformed the eternal universe hypothesis from philosophical speculation into testable science. In the coming decades, these instruments may finally provide the evidence needed to determine whether humanity lives in a cosmos with a birthday or in an eternal dance of matter and energy that has been playing out across infinite time, with no beginning and no end, only endless transformation and endless possibility. At the edge of all human understanding, where mathematics meets mystery and science dissolves into wonder, the eternal universe hypothesis reveals its most profound implications, not in the equations that describe cosmic evolution, but in what those equations mean for conscious beings who find themselves swimming in an ocean of infinite time. The question of whether the cosmos had a beginning transforms from a problem of astrophysics into a meditation on the deepest nature of existence itself. If time truly stretches backward without limit, then humanity confronts a reality more strange and beautiful than any creation myth ever conceived. In an eternal universe, death becomes not an ending but a transition, a temporary dissolution of the patterns of matter and energy that constitute individual consciousness, patterns that must eventually reform in identical configurations across the infinite expanse of space and time. Every moment of joy experienced by a human mind, every instance of suffering endured by conscious beings, every love shared between individuals becomes not a unique occurrence, but an eternal reality, recurring in endless variations throughout the boundless architecture of time. The implications cascade through every aspect of human experience like ripples spreading across an infinite pond. In a cosmos where every possible arrangement of atoms must occur not just once but infinitely many times, identical copies of every person must exist scattered throughout space and time. Somewhere in the infinite past, perfect duplicates of every individual have lived identical lives, made identical choices, and pondered identical questions about the nature of existence. Somewhere in the infinite future, those same patterns will emerge again, living the same experiences with the same sense of novelty and discovery that marks conscious experience in this present moment. This infinite repetition challenges the very foundations of human agency and meaning. If everything that can happen must happen infinitely many times, then the decisions that define individual identity become strange kinds of illusions. The choice to pursue knowledge rather than ignorance, to extend compassion rather than cruelty, to seek understanding rather than comfortable delusion, all of these apparent exercises of free will have been made by identical minds in the infinite past and will be made again by identical minds in the infinite future. Yet this apparent predetermination operates at such a vast scale that it becomes irrelevant to lived experience. The identical copies scattered throughout infinite time are separated by distances so vast and durations so long that they remain forever isolated from one another, each experiencing their choices as novel and meaningful despite their infinite repetition. Free will, if it exists at all, becomes a local phenomenon in an eternally predetermined cosmos wheel and significant within the bounded experience of individual consciousness, even if it represents merely one predetermined thread. In the infinite tapestry of possible experiences, the question of ultimate meaning undergoes an equally profound transformation in an eternal universe. Religious and philosophical frameworks that depend on creation, on a moment when existence began and might therefore require a creator, must grapple with the possibility that existence simply is, that the universe requires no external cause, because it never came into being. The deepest question that has haunted human thought since consciousness first turned inward upon itself shifts from why is there something rather than nothing, to why should there be nothing rather than something. In an eternal cosmos, existence becomes not a mystery to be solved, but a fundamental characteristic of reality itself, as basic and irreducible as the mathematical relationships that govern the behavior of matter and energy. The search for ultimate origins dissolves into the recognition that the concept of ultimate origins might itself be a category error, a question that assumes inappropriate frameworks of cause and effect, beginning and ending, that simply do not apply to the deepest levels of reality. Science itself takes on new significance when viewed from the perspective of infinite time. Human knowledge, accumulated over millennia of observation and experimentation, becomes part of an infinite pattern of discovery and forgetting, learning and loss that has played out countless times before and will play out countless times again. The scientific method, that systematic approach to understanding reality that has transformed human civilization, has been discovered and forgotten infinitely many times in the infinite past, and will be rediscovered infinitely many times in the infinite future. Yet, this infinite repetition of scientific discovery does not diminish its significance, but reveals its true nature. If consciousness is a natural feature of an eternal universe, if awareness emerges spontaneously from the interaction of physical forces whenever matter and energy organize themselves in sufficiently complex configurations, then the universe becomes not a machine but an infinite dreamer, cycling through endless possibilities for experience and understanding. In this vision, scientific knowledge represents not the accumulation of facts about an external reality, but the universe's ongoing process of self-discovery. Each conscious observer becomes a focal point through which the cosmos experiences and understands itself, a temporary vantage point from which infinite reality contemplates its own nature. The questions that humans ask about the origin of time become the universe asking those questions about itself through the medium of conscious minds embedded within its structure. The eternal universe hypothesis forces a confrontation with the possibility that time, change, and causation, the fundamental frameworks through which conscious minds understand existence, might themselves be emergent properties of something deeper and more mysterious. Rather than standing at the center of creation, conscious beings find themselves as temporary patterns in an eternal dance. Notes in an infinite symphony that has been playing since before forever began and will continue long after forever ends. This realization might initially seem to diminish human significance, reducing individual lives to brief flickerings in an infinite expanse of time. But deeper reflection reveals the opposite truth. If the universe is indeed eternal, then consciousness represents something genuinely remarkable, not because it is rare or unprecedented, but because it is the means through which infinite reality becomes aware of itself. Each moment of awareness, however brief, however localized, however repeated across infinite time, remains precious and irreplaceable because it represents a unique perspective on eternity. The configuration of matter and energy, thought and feeling that constitutes any individual consciousness emerges only once in precisely that form, at precisely that moment, with precisely that mixture of hope and uncertainty, knowledge and ignorance, love and loss that defines the texture of lived experience. While identical patterns might recur infinitely throughout space and time, each instance represents a fresh emergence of awareness, a new opening through which the universe experiences wonder and asks questions about its own nature. Perhaps this is the deepest truth revealed by contemplating an eternal universe, that consciousness, emerging from the endless dance of quantum fields and cosmic forces, represents something genuinely miraculous, even in an infinitely old cosmos. The capacity for wonder, the ability to ask questions about existence, the experience of beauty and meaning and love, these phenomena become not accidents of cosmic evolution but fundamental features of reality itself. As natural and inevitable as the formation of stars and galaxies in the infinite expanse of space in an eternal universe, human beings are neither the first nor the last to ask these ultimate questions about time and existence, but they are the first to ask them in exactly this way, at exactly this moment in cosmic history, with exactly this unique combination of scientific knowledge and philosophical uncertainty that defines the current epoch of human understanding. That they can ask such questions at all, that matter and energy can organize themselves into patterns capable of contemplating infinity, might represent the closest thing to a miracle that an eternal universe allows, whether time had a beginning 13.8 billion years ago or stretches infinitely into the past. Conscious observers remain capable of wonder, discovery, and love. The cosmos might be infinite in temporal extent, but each moment of awareness remains finite, bounded, and therefore precious. In the face of eternity, perhaps the appropriate response is not despair at human insignificance, but gratitude for the opportunity to participate, however briefly, in the universe's endless conversation with itself about the nature of time, existence, and meaning.